Good evening, ladies and gentlemen. Good evening, Professor. I'm presenting my project for TPG 3700 project with regard to transportation engineering and pavement design for course of advanced diploma in civil engineering at UNISA. My name is Andrew Mature. So the topic that I'm going to cover are basically the honor pledge, executive summary, introduction, locality, classification, and geometric as they are indicated here up to drainage conceptual design. The honor pledge, it represents and acknowledges the ownership of my work, since this is my own work that I've worked on, and it is basically no any assistance that I got from anyone or any student. The executive summary basically it covers the purpose of the project, which is the project with regard to attainment of or passing a module called TPG 3701 at UNISA. The road that we are going to be analyzing is called Valencia Road. It's 34 kilometers. So this road was designed previously having 10 years analysis period. So the first structural design period was 7 years, and the second structural design period was for 3 years. The road is to be improved now from category C to category B, which means we're also going to extend its lifespan to almost 20 years. Execution to be done in 4 phases. So 3 kilometers will be starting this year, and the rest will be allocated until 2025, 2026. The locality and ownership of the road. The road is located under Vembe Municipality District and is owned by Roads Agent Limpopo Rao. The starting and end points of the road are shown here and are also indicated in my project. This is the aerial view or topograph view of the road that we're going to be designing. That's where it's lying basically. So this road is more of like an ARA type of a road, the original road that is connecting this community to their respective township. The classification and traffic estimation. The traffic is estimated to be in class EC1 to EC10. The daily equivalent vehicle unit is actually 600 to 10,000 that we expect. This 1,000 is a mistake, but basically it's up to 10,000. So the geometric designs that we're going to use, the number of lanes is basically 4. The carriage width lane for the design is 3.7, and the road has got 1 meter shoulder, which is tarred, and another 1 meter, which is not tarred, which is gravel. So all in all, the road has got 18.8 meters. The crossflow of the road is 2%, and the super elevation is 4%. This is according to TRH 17 and TRH. So basically, on the horizontal alignment, we're checking the information that we were given by the AutoCAD Civil Design, sorry, AutoCAD Civil 3D when we designed the road. So basically, we got for horizontal alignment, we got the beginning of a curve at 0.293, so 0 is 293.86 meters. The coordinate values are these ones. Then the end of the curve was at 415. The coordinates are also respectively these ones. So we carried the joint to check if the we carried the joint to check the total straight line that connects these 2 points. And we also checked these points with regard to the AutoCAD. So on the AutoCAD, we got it as 120.45. Then on the join when we carried just 120.31, which is almost equal here and there. Then the length of arc, when we measured it, since we put a circle on the AutoCAD to check the radius of the circle that describes this curve, this horizontal alignment, we got it the radius as 281.042, and the deflection angle we got it as 24 degrees 42 minutes 24.83 seconds. However, this 281 is actually okay, since the design according to TRH 17 it stipulates that for a horizontal curve you need about 210 meters with a design speed of 8 kilometers per hour. Then we also check the vertical alignment. On vertical alignment, we did the calculations, but however, for this presentation, we focus much on the TRH17 and to check if the vertical alignment is okay. So the stopping side distance at 80 kilometers basically is given as 140 approximately on TRH17. When we checked that the stopping side distance is less than the curve length that we're having, so we use this formula to check if this curve is okay. So the actual curve for side distance that we got was 280.8, which is bigger than 140, which means it's okay. Then on subgrid design, we're given the average CBR ratio percentage, California bearing ratio, which was 18.5. So with this one, we deduced the design CBR, which we got as 17.1%. So when we checked that this road is actually falling under SG1 because it's greater than 15, so the road only needs to be ripped and recompact to 150 millimeter G7 for the subgrade. Then the image one here is just showing us when we were entering the information or when we were importing information into AutoCAD. So basically, when you start AutoCAD, you need to do your settings. The settings that were given by the surveyor are Johannesburg 94LO33 and its South African coordinate system. So if you can check here, it shows the Republic of South Africa, Johannesburg 90LO33. Then when we import, you come into here, create points, then import. When you import points, now we're taking these points, actually we're given them in a form of a TXT file from the surveyor. So these are the points that we're importing. So when you import points on the AutoCAD, it must pick and tick the green here to show that the points are okay. And also it must show you the points as they are here. Then when you move on, once you are done with that, you close it. But to visualize this road now, you need to come and zoom and click the zoom function for the AutoCAD. So basically, if you check this alignment, and the alignment we got on the alignment that was shown on our topographical survey is identical. Now we started doing the AutoCAD designing by putting in lines. Since we start by lines, then after that we add curves. Now, after that, we created a surface, which is surface EG, the surface EG by adding all these points. When we add the points now, the AutoCAD Civil 3D created the surface, which is this surface. This surface, it shows contour lines within this region, the area that we're given by the surveyor. Then from there, we create a horizontal alignment, which was called AB. After that, so we created, this is now the horizontal alignment. If you can check on my PDF drawings, you can clearly see it. Then from there, we created the surface. Now we're creating the surface profile, which is like we're profiling the land. The land. We need the cross-sectional view of the land that is existing. So basically, this is how we got it. And here, this is the generation of it. This is the cross-sectional view of the land. After that, we started adding the profile for our surface where we want our road to be in. So the road is actually the blue one, which is this one following our ground level that we're given. Then to generate the corridor, you need to do an assembly. An assembly is this one. Now, this assembly has got a thickness of 490 millimeters, and it has got side slopes for V drains of 1 in 4. After running our assembly, we managed to generate our corridor, which is this corridor basically, which is the road alignment. So with that, it shows we can easily generate all the quantities now that we need, like the cut and fill, the muscle diagrams, which are illustrated on my annexures that are on the drawing. Now, on the proposed drainage system, since we know that this road is basically having some V drains that are running on the sides. So basically, those V drains, what we checked were two we're checking sections which are having two highest points. So within an area that has got two highest points, we must have a lowest point. So on those lowest point, that's where we mm, inserted our culverts. The V drain will work basically as collecting water from the main road by surface runoff, which will then be collected to the V drain by collected by the V drain. Then it will be channeled to the lowest point, which is where we inserted our culverts.